In today's lesson, we're going to look at solving exponential and logarithmic equations. Our objectives today is to solve logarithmic and exponential equations using a variety of strategies. These include using properties from yesterday, one-to-one properties that we'll talk about, rewriting exponential to logarithmic form in order to solve, and lastly, taking the natural log of both sides. First, let's talk about one-to-one relationships. Here's an example one-to-one relationship. If I have an exponential function, say base a, and it's raised to some power of x, but it's equivalent to another function, base a, and it's raised to some power of y. Since there's an equal sign in between, and the bases are the same, this means I can set the exponents equal to each other and solve for whatever variable I need to do. This is true for logarithms. In fact, if I have log base a of x, again, equal to log base a of y, since again, there's an equal sign involved and they're the same base, that means I can set the insides equal to each other and solve for whatever variable I need to. These are both examples of one-to-one relationships. So when we're solving logarithmics and exponential equations, we kind of want to run through a checklist. Can we first use log properties to simplify? These are the properties that we learned from yesterday. So properties such as addition goes to a multiplication or a division goes to a subtraction, those kind. We also look for one-to-one properties. These are the properties that we just looked at the slide before. If those two don't work, then we look at rewriting this equation into either exponential or logarithmic form, depending on the situation. And our very last resort is if we can't do any of the top three, we take the natural log of both sides, which allows us to bring the exponent down, and then we look at solving that way. Usually this is for solving exponents only. So let's take a look at our first example. If we run through our checklist, we have 4 raised to the x plus 2 power equals 16 raised to the x minus 3 power. If we look at the first case, notice that we really can't use any logarithmic properties because there is no logarithms at all. In the second case, we really can't use one-to-one properties yet. However, I believe I can write 16 as a base 4, or I could even write both 4 and 16 as base 2s. Since 16 is a base 4, I can write that as 4 squared. Remember, I still have the power of x minus 3 outside, and it's still equal to the other side of 4 to the x plus 2. What that allows us to do now is, since we've written it in the same base of 4, I can use properties of exponents by multiplying the 2 to each part of the exponent in the right side. So in this case, I would get 4 raised to the 2x minus 6 power, and it's still equal to 4 to the x plus 2 power. Now that I've written them in the same base, now I can use the one-to-one properties. Since I have both base 4s, I can set the exponents equal to each other and solve for x. Subtracting x to both sides, and then adding 6, I get my final answer of x equals 8. Now remember, you can check your answers with any of these by subbing it back into the original function just to make sure we're right. So for our next example, we have solve log base 5 of x squared plus x equals log base 5 of 20. Again, notice we don't have sum between logarithms or a difference between two sets of logarithms, so we really can't use logarithmic properties here. But I believe I can use one-to-one properties because of the fact that we have both the logs with the same base, and there's an equal sign in between. This means I can set the insides equal to each other and solve for x. If I do this, I have x squared plus x equals 20. Notice we have a quadratic function, and any quadratic function we like to set equal to 0 to solve. So if I subtract 20 to the other side, I get this. I believe this is factorable. In fact, if I factor this trinomial out, it becomes x plus 5 and x minus 4. So when I solve, my two answers would be x equals -5 and x equals +4. If I check my answers, if I sub in 4, I get log base 5 of 4 squared plus 4 equals log base 5 of 20. If I simplify, I have log base 5 of 20 equals log base 5 of 20. So therefore, 4 checks out. And if you do the same thing with 5, you'll notice that, -5 will also work too. So both of these are our answers. For example 3, we have log base 2 of 5 equals log base 2 of 10 minus log base 2 of x minus 4. If I run through my checklist here, notice that I think I can use logarithmic properties right away. In fact, since there's a subtraction sign in between two separate logarithms, I can then condense this into a single logarithm. And remembering properties from yesterday, this means any subtraction I can write as a single logarithm as a division and write it as 10 over the x minus 4. Now that I've condensed it using properties, I can now use my one-to-one properties here. Because of the fact I have log base 2 equals log base 2, I can set the insides equal to each other and say that 5 equals the 10 over x minus 4 and try to solve for x. Here, notice we have a fraction. And to get rid of a fraction, we can multiply the x minus 4 to both sides. When I do that, on the right-hand side, they cancel. On the left-hand side, I can distribute the 5 through, becoming 5x minus 20 equals 10. Lastly, solving for x, adding 20 to both sides, I get 5x equals 30, and dividing by 5, I get my final answer of x equals 6. And again, checking our answers, we'll see that x equals 6 works, so therefore that's our solution. Now I want you guys to try some problems on your desk. Use your marker and rag near you and see if you can work out both of these problems. I'll give you a hint. In part A, you may need to change the base before you use one-to-one properties. In part B, you may want to look at using properties of exponents before, again, you use the one-to-one properties and set the two insides equal to each other. Good luck. So in the first case, you should have written 32 as a base 2 as 2 to the 5th, and 4 as a base 2 as 2 squared. Using properties of exponents, I can distribute the 5 through the left side and the 2 to the right side because we multiply the exponents. And when we do that, I get 2 to the 5x minus 5 power equals 2 to the 2x plus 10 power. Since they're the same base, I can use a one-to-one property and set the exponents equal to each other. So I have 5x minus 5 equals 2x plus 10, and so I believe you should get an answer of x equals 5 in the end. For the next one, I can use properties of logarithms to condense this to a single logarithm. Since this is an addition, I can write this as log base 7 of x cubed times x. I can write that as a multiplication. It still equals the log base 7 of 16 on the right side, but now I can multiply those together and it becomes log base 7 of x to the 4th equals log base 7 of 16. Since they're the same base, I can now set the insides equal to each other using the one-to-one properties and set x to the 4th equals 16. And to solve this, I would have to take the 4th root of both sides, which leaves me just x on the left side, and what I'm left with on the right side is 2. And there's my answer. So let's take a look at this next example. Here's a little different. Notice that we have 2 natural log of x equals 18, and our goal is to solve for x. Notice we can't really use any logarithmic properties here because there's no sum or difference between them. We also can't use any one-to-one properties because, really we don't have any, there's not a natural log on both sides. And so our next resort is sort of looking at that third one, rewriting exponential to logarithmic form. But before you do this, you always want to isolate the log by itself. Notice we have 2 times the natural log in front. So to get rid of that 2, if I simply divide 2 to both sides, I'll have natural log of x equals 9. Now that the natural log is isolated, let's rewrite this in exponential form to help us solve. Remember, with natural logs, there's a hidden base e here. And so if I change this to exponential form, what this would look like is e to the 9th power is going to equal x. Notice we basically already have our answer now. It's just e to the 9th, which ends up being about 8,103.08 if you do this on your calculator. Remember, to find e on your calculator, you have to go second natural log, and that should help you access the e button. And again, you can check your answers by typing that in, but that's our final answer here. Here's another unique example. For this one, we have solve 3 to the x equals 7. So if we run through our list again, we don't have any logarithms to deal with, so we're not going to use any logarithmic properties. We don't have the same basis here, so we can't use one-to-one properties. If we try rewriting in exponential to logarithmic form, I guess we'd have log base 3 of 7 equals x. But again, this is something that we don't know and can't evaluate, so I guess we're on our last resort, which is taking the natural log of both sides. So what it means to take the natural log of both sides is if I have 3 to the x equals 7. If I take the natural log of both sides, remember, whatever you do to one side, you have to do to the other. What happens is we can use one property of logarithm that allows us to sort of bring that exponent down in front, which is what we're trying to solve. So by taking the natural log of both sides, it now reads x times natural log of 3 equals natural log of 7. And since we're trying to get x by itself, it makes sense that we would divide by the natural log of 3 to both sides, and our answer would become x equals natural log of 7 over natural log of 3. When you do this on your calculator, I believe you get 1.77. Just like before, I want you guys to try some problems here. Work these out. In the first one, I'll give you a suggestion. Try to isolate the x to the 8th first. So maybe add 1 to both sides. And then it's going to be like our last example. In the second case, again, try to isolate the 2e to the 2x. So if I subtract 1 to both sides, and then look at how to get rid of that 2 so that you can isolate e to the 2x and then change it to logarithmic form. So take some time to work both of these out, and we'll check our answers in a little bit. Good luck. So in the first one, if you added 1 to both sides, we get 8 to the x equals 4.4. Now that the 8 to the x is isolated, I really can't use any log properties. I can't use one-to-one. Changing it to logarithmic form won't really help us, so the last resort is taking the natural log of both sides. So if I take the natural log of the left and natural log of the right, what happens is we can use that property of logarithms and bring that exponent of x down in front. So now it reads x times the natural log of 8 equals the natural log of 4.4. And then again, in order to solve for x, dividing the natural log of 8 to both sides, what I have is x equals the natural log of 4.4 divided by the natural log of 8. And using my calculator, you should get an answer of 0.713. Now for the next one, if I isolated the 2e to the 2x by subtracting 1 to both sides, I get 2e to the 2x equals 6. Before you change things into logarithmic form or try to take the natural log of both sides, we always want to isolate that base by itself. And to do this, let's divide that 2 to both sides. It will cancel on the left-hand side, and what I'll have is e to the 2x equals 3. Now that I have it isolated, it could either A, change to exponential form, or B, take the natural log of both sides. It's your choice. If I take the natural log of both sides, what happens is, again, that exponent of 2x gets brought down in front, and what I have is 2x times the natural log of e equals the natural log of 3. And remember, the natural log of e is just 1. So in order to solve this, all I got to do is divide by 2 on the left-hand side and the right, and what I'll have is x equals the natural log of 3 divided by 2, which ends up being 0.55. Now that we've tried some basic cases on solving exponential logarithmic functions, let's look at a couple harder cases today. Now, in order to solve some of the unique cases here, we first need to look at some prerequisite skills. And the big thing is being able to factor, but factoring trinomials that look like these two. Now, we're used to the case of factoring sort of trinomials with x squared, so such as x squared minus x minus 6. Looking at factors of -6 that add up to -1, it becomes this. We're very quick at these. But we can do sort of a similar factoring method with even trinomials with degrees of 4. You still want to look at factors of -35 here that add up to -2. And in this case would be -7 and +5. But now if I factor, I'm not going to put x in both the boxes. I'm going to put x squared, because the only way I can split up x to the 4th is really x to the 3rd times x, or x squared times x squared. And since the factors that add up to -2 are -7 and 5, I have my answer for A. This would be the factored form for A. Similar to B, if I look at factors of 28, -28 that add up to +3, right away I see +7 and -4. And since this is y to the 6, there's several ways I can split this up. But usually it relates to your middle term of y to the 3rd. And so to split up y to the 6, I can write it as y to the 3rd times y to the 3rd. And since the factors of -28 that add up to +3 are +7 and -4, that would be the fully factored form of part B. So again, these are some prerequisite skills to solving these unique equations that we'll look at here in a second, but you got to know how to factor these higher degrees first. Now for this first one, we really don't need any factoring techniques. You'll see it with the next case. But notice if we run through our checklist, we can't use really any logarithmic properties. There's no way we can write 3 as a base 2 or 2 as a base 3, so we're kind of stuck there. If we rewrite it in logarithmic form, that'll kind of get us stuck. So the last resort is, again, taking the log or taking the natural log of both sides. If I do this, taking the natural log of the left side, again, that entire exponent gets brought down in front, but now same with the right side. So using properties of exponents, if I take the natural log of both sides, that 6x minus 3 gets brought down in front, and the 4 minus 4x gets brought down in front. Remember when you bring that down in front that it's grouped inside parentheses. So now it reads 6x minus 3 times the natural log of 3 equals 4 minus 4x times the natural log of 2. And remember, our goal is to solve for x. So we're going to get some decimals here. In fact, if you're trying to isolate x, the goal is to get it by itself. So if I get rid of these sets of parentheses by distributing the natural log through, I'm going to have natural log of 3 times 6. Rounding to 2 decimal places, it gives me 6.59, and I still have that x, minus, if I take natural log of 3 times 3, I get 3.295 if I go 3 decimal places. Let's do the same on the left-hand side. Distribute the natural log of 2 through. So 4 times the natural log of 2 gives me 2.77 minus 2.77x. Now that we've sort of gotten rid of parentheses, the next step would be to isolate x by itself. So if I add the 2.77x with the other x's on the other side, so this gives me 9.36x minus 3.295 equals the 2.77. Again, isolating x by itself, I would add this 3.295 to both sides. And I have 3.36x equals 6.061. And then in order to solve for x, if I divide by that 9.36 to both sides, I'll have my final answer of 0.648. So these aren't too unique. It's just the fact that you got to take the natural log of both sides, and now you're just dealing with a lot of decimal answers. So do your best to round. And again, this was to the nearest hundredth place, so that's why I was using at least 2 decimal places in my answers. So this is sort of, I guess you could call it one of the harder cases of solving, because this relates to the factoring prerequisite skills that we talked about earlier. Notice that this kind of looks like it could be factored. In fact, it can be. We can't use logarithmic properties here. We can't use one-to-one. If we try to rewrite, it's going to be very difficult for us to even rewrite. And taking the natural log of both sides just messes things up for us because you have multiple terms. So our last resort is sort of using factoring techniques to solve. Now, it's hard for us to see it is factorable unless we kind of do something unique. Here's what I'm going to do. Whatever the middle term is, I'm going to let another variable equal that. Let's say y. Let's say y equals e to the x. If I allow y equal e to the x, I can rewrite this equation on the left-hand side to be y squared minus y minus 2 equals 0. Because if I sub in e to the x, we get the same equation back. When it's in this form, it's a lot easier for us to look at and factor. In fact, this factors into y minus 2 times y plus 1 equals 0. And the two solutions from this would be y equals 2 and y equals negative 1. But that's not our real solutions. We originally let y equal e to the x. So after we sort of factor and solve, we can now reintroduce the fact that e to the x equals y. So the two equations below of y equals 2 and y equals negative 1 now reads e to the x equals 2 and e to the x equals negative 1. And so now you're just solving these two separately. So if you take the natural log of both sides and solve, I believe the first one you get an answer of 0.693. And if you try to solve the other one, you're not going to be able to because we can't take the natural log of any number that's negative. In fact, if you just try to think of e to what power is negative 1, we don't get any answers from that. So the only answer here is going to be 0.693. So last two problems of the day. I do want you to try these on your desk if you want. You can work together in pairs, but in a little bit we'll go over the answers. Good luck. So in the first example, we really can't use any logarithmic properties, no one-to-one, so we're kind of just jumping right to taking the natural log of both sides. So if I take the natural log of the left and natural log of the right, what that allows me to do is use properties of logarithms now to bring that exponent down in front of the equation. Now remember, when you bring it down, we group it in parentheses. And now our next goal is to really solve for x. So if you distribute the natural log of 4 through, you get 1.38x minus 4.16 equals, if you distribute the natural log of 6 through, you get 3.58x minus 1.79. And balancing both sides and trying to isolate x by itself, I believe you should get an answer of negative 1.08, 2 decimal places. Now for the last one, again, it's a factorable one. So if I let my y equal e to the x, then I can rewrite this as y squared minus 3 times y plus 2 equals 0. A lot easier to look at, a lot easier to factor. This factors into y minus 2, y minus 1. Our two answers from this would be y equals 2 and y equals 1. But remember, we let y equal e to the x. So if I sub that e to the x back in, this really means solving e to the x equals 2 and e to the x equals 1. Taking the natural log of both sides, you'll get your answer because bringing the x down, natural log of e is just 1. So my answer becomes natural log of 2, whatever that decimal is. And in this case, if I do the same process, you'll get the natural log of 1 for your answer there. So this concludes our lesson for today. The recorded lesson is online Canvas, so you can find that in the Chapter 3 module if you ever want to look back at some of these examples. But tomorrow in class, we're going to look at review. And here is your homework that is due Monday. Remember, your Chapter 3 check-in will be due on the actual test days. So we'll be reviewing on Friday, and we'll take the test on Monday. Good luck, and enjoy your work time.